The first example on the galvanic cells worksheet gives you a silver-nickel galvanic cell. The first question asks you to write the balanced reaction that occurs. So the first thing we need to do is look up the two reduction half reactions and their half cell potentials on an SRP table. The silver reduction reaction has a half cell potential of 0.80 volts. The nickel half reaction has a half cell potential of negative 0.23 volts. How do we use this information to determine the reaction that spontaneously occurs? For two given reduction half reactions, a more positive half cell potential goes with the more easily reduced species. In other words, the half reaction with the more positive half cell potential is actually reduced. The other half reaction will be the oxidation half reaction. It will occur in the opposite direction from how it's currently written. Before we add half reactions together, we make their number of electrons balance. So we need to multiply the silver half reaction by 2. Then we can put the two half reactions together. So silver ions are getting reduced to silver atoms, and we need 2 of them. Nickel atoms are being oxidized to nickel ions. Now we need to write the reaction in line notation. In line notation, we use a double bar in the middle to separate the oxidation half reaction from the reduction half reaction. Make sure you see the difference between that and the arrow in a standard chemical equation. An arrow separates the reactants from the products. The double bar in line notation represents the physical separation of the two half cells. For this reaction, the oxidation process is nickel atoms becoming nickel ions. The reduction process is silver ions becoming silver atoms. 2 things to remember about line notation. 1, chemists do not include coefficients in line notation. And 2, there should always be a solid electrode on either end of line notation, both at the beginning on the left and at the end on the right. If you don't have a solid electrode listed on each end, something's not right. The next question asks you to calculate cell potential. We do that by using the reduction values from the SRP table. Take the value for the reduction half reaction and subtract the reduction value for the oxidation reaction. Remember, we do not multiply half cell potentials by coefficients. So in this example, 0.80 minus negative 0.23 is 1.03 volts. Now, to calculate delta G for the reaction, we use the equation delta G equals negative N times F times E naught for the cell. N is the number of electrons transferred. When we balanced the number of electrons between the two half reactions, how many electrons did we get to? 2. That's our value for N. F is a constant. For every mole of electrons transferred, 96,500 coulombs of charge pass through. We just calculated E naught for the cell to be 1.03 volts. The product of these values results in delta G equal to negative 199,000 joules, or if you switch it, negative 199 kilojoules. Next, you're asked to do some labeling of the illustration. When we figured out the thermodynamically favorable reaction, we determined that silver was being reduced and nickel oxidized. Reduction occurs at the cathode. Oxidation occurs at the anode. Electrons always travel from anode to cathode. What happens to the mass of the silver electrode as the cell runs? In that half cell, silver ions from the solution are becoming silver atoms on the electrode. So the mass of the silver electrode increases during the reaction. In the other half cell, nickel atoms that are part of the solid metal electrode are oxidizing, coming off the solid electrode and becoming ions in solution. So the mass of the nickel electrode decreases as the cell runs. Finally, what are the ions of the salt bridge doing? In the cathode compartment, positive silver ions are being removed from the solution. That positive charge deficit is replenished by positive sodium ions from the salt bridge moving into the cathode half cell. In the anode compartment, positive nickel ions are being added into the solution. This buildup of positive charge can be balanced out by the movement of negative nitrate ions from the salt bridge into the anode compartment. The ions from the salt bridge are not part of the redox reaction that's occurring. The purpose of the salt bridge is to maintain charge neutrality in both half cells. In the cathode, that means replacing positive charge into solution. And in the anode compartment, that means adding negative charge to balance out the positive charge that is being added by the redox process. The second example on the worksheet gives you two half cells and asks you to write the reaction in standard form and in line notation. Look up the two half cell potentials. The half reaction with the more positive half cell potential undergoes reduction as written. The other half reaction undergoes oxidation, so the reaction is flipped. Multiply the iron half reaction by 2, so the number of electrons are equal. Then combine the half reactions. The result is 2 iron 3 ions reacting with a zinc atom to produce 2 iron 2 ions and a zinc ion. Now we need to write this reaction in line notation. Let's take a second, though, and look first at the physical setup of this galvanic cell. Say we put the zinc half cell on the left and the iron half cell on the right. Understand that the external wire has to be connected to a solid that is immersed in the solution. For the zinc half reaction, solid zinc is part of the reaction, so a zinc electrode is used. But in the other half reaction, both the reactant and the product forms of iron are ions in solution. You can't attach a wire to ions in solution. So what solid do you use? You use an inert electrode, often platinum. By inert, we mean a metal that will not react with anything else in the system. How do we show that in line notation? We still have to draw the double bar to indicate the physical separation of the oxidation and reduction half reactions. In this case, the first half of our line notation is same as always. Solid zinc, a single bar, and the zinc ion. For the other half reaction, though, we have iron 3 ions becoming iron 2 ions. Both are in the same state, ions in solution, so they're separated by a comma. but we have to have a solid electrode on the end of line notation. So then we add the single bar, then PT to represent the inert platinum electrode.